Welcome to your ultimate thermal physics exam review session. I am beyond thrilled you're here. Today, we're going to act as your personal mentor, taking what can honestly feel like a massive, intimidating mountain of physics formulas and breaking them down into easy, tangible, real-world concepts. Seriously, by the end of the study guide, you are going to have the total confidence you need to tackle any exam question on heat transfer, specific heat, and thermal expansion. You've totally got this. So here is our game plan for this review bootcamp. We're going to start with the foundations of temperature and expansion, move into the math of specific heat, navigate those tricky phase changes, map out heat transfer mechanics, and then finish really strong with some final exam review practice. All right, let's jump right into section 1, temperature and expansion, the foundations. Okay, first things first, we need to clear up the biggest hurdle students constantly face, confusing heat with temperature. Listen, heat is the actual energy being transferred between systems, right? But temperature is just the relative measure of that hotness or coldness. If we look at how we measure that hotness across the different scales, specifically the ice point and steam point of water, you'll notice something interesting. While Fahrenheit has 180 intervals between freezing and boiling, Celsius and Kelvin both have exactly 100. They share the exact same unit size, it's just that they have completely different starting points. Now that actually brings us to a really fascinating piece of history. Have you ever wondered how scientists figured out absolute zero, like literal zero on the Kelvin scale, without actually freezing something to that extreme point? Well, they measured the pressure of low-density ideal gases at various temperatures and noticed this perfectly linear relationship. It was a straight line. So by mathematically extrapolating that straight line backward on a graph until the pressure reached zero, they hit exactly negative 273.15 degrees Celsius. And that absolute theoretical minimum became the entire foundation of the Kelvin scale. Pretty clever, right? Let's ground all this in reality with thermal expansion. Because molecules literally jiggle and move more when they're heated, most substances expand. And this isn't just some abstract textbook equation. It's exactly why a blacksmith heats an iron ring before fitting it onto a wooden cartwheel. As it cools, it contracts for a perfect, impossibly tight fit. It's why engineers absolutely must calculate thermal stress, leaving those little gaps in railway tracks so the steel doesn't dangerously buckle and bend under the hot summer sun. Hey, it's even why running a super tight metal jar lid under hot water at home magically loosens it up. Okay, moving right along to section 2, specific heat and calorimetry, the math of heat. Please don't let the math scare you here, because calorimetry is essentially just balancing a simple budget. Let's run through a quick specific heat capacity cheat sheet. Specific heat is just the amount of heat required to change the temperature of 1 kilogram of a substance by 1 Kelvin. Take a look at water, 4186 joules. That is massively high compared to something like copper or glass. Use this as a mental shortcut. Because water takes so much energy to heat up and cool down, our oceans perfectly regulate global climates. Meanwhile, deserts, which lack all that water, bake during the day and freeze incredibly cold at night. So, when you face a classic exam word problem, like, say, dropping a hot aluminum sphere into a copper calorimeter filled with water, just take a breath and follow 3 simple steps. Step 1. Calculate the heat lost by the hotter object using its mass, specific heat, and temperature change. Step 2. Do the exact same thing for the heat gained by the colder water and its container. And Step 3. Set the 2 equations equal to each other. Heat lost always equals heat gained. Solve for your unknown variable, and boom, you've just aced the question. Let's tackle section 3, phase changes and latent heat state transformations. I know this is a notoriously tricky spot for a lot of students, but stick with me because you already have all the tools you need. The absolute most crucial point here is busting a massive student misconception: temperature does not rise during a phase change. Seriously, when ice melts at 0 degrees Celsius or water boils at 100 degrees, the temperature completely plateaus. All that thermal energy you're pumping in, it's going strictly into breaking atomic bonds and transforming the physical state of the matter. We call this latent heat, which literally means hidden heat. And here is a real-world example that brilliantly illustrates why latent heat matters. Compare boiling water at 100 degrees Celsius to steam at the exact same temperature. The steam is far, far more dangerous. Why? Because to turn that boiling water into steam, it had to absorb the latent heat of vaporization, which is a massive 22.6 times 10 to the 5th joules per kilogram of extra hidden heat energy. When that steam hits your skin and condenses, it releases all that extra energy at once, causing burns that are much more severe than boiling water alone.
Now, let's see how this builds into an incredible concept called the triple point. By plotting pressure versus temperature on a phase diagram, scientists found a precise, almost magical coordinate where the solid, liquid, and vapor phases of a substance coexist in perfect thermal equilibrium. For water, this happens at exactly 273.16 Kelvin. Because this natural phenomenon is so incredibly precise, scientists actually use the triple point to establish standard, unvarying reference points for our modern temperature scales. The cool thing is, we can manipulate these phase changes right in our own kitchens using pressure. Think about how a pressure cooker speeds up your food prep. It traps steam inside with an airtight lid, right? That increases the internal pressure well above our normal 1 atmosphere. And because the pressure is higher, the boiling point of the water is forced way above its normal 100 degrees Celsius. The water gets so much hotter before it finally boils, which means your food cooks significantly faster. Next up is Section 4. Heat in motion, transfer mechanics. We're going to look at the 3 distinct modes of how heat travels: conduction, convection, and radiation. Let's start with conduction, which is heat transfer through physical contact. Think about this through the lens of modern building architecture. Imagine a multi-layer wall or roof. The blistering solar heat hits the outer concrete, which begins conducting that heat inward. But then, the heat hits a plastic foam insulation layer. Because gases are incredibly poor thermal conductors, the little trapped air pockets within the foam effectively stop the conduction process in its tracks. This is an intentional design choice that totally protects the interior from extreme temperatures. Beyond conduction, we have convection. That's heat transfer through the actual motion of fluids, like heating systems effectively circulating steam to warm large buildings, or natural convection currents creating our planet's massive global trade winds. And finally, there's radiation, which requires no medium at all. It's how the sun's energy reaches Earth through the vacuum of space. Everyday thermos flasks are actually genius because they use vacuums to stop conduction and convection and shiny silver coatings to reflect that thermal radiation, keeping your coffee piping hot all day. All right, we have made it to Section 5, Final Exam Review Practice. You now have the formulas, the vocabulary, and the conceptual tools required to absolutely ace your physics exam. So let's put that confidence to the test. Here's a quick check practice question for you. Based on everything we've covered about temperature and density, why do lakes freeze from the top down instead of the bottom up? Take just a second to think about it and apply what you've learned. Okay, if you guessed the anomalous behavior of water, you hit the nail right on the head. Unlike most substances that continually shrink and contract as they cool, water is actually most dense at 4 degrees Celsius. As water cools below 4 degrees toward freezing, it bizarrely expands and becomes less dense. So this cold, lighter water floats right to the top and freezes into a solid, protective ice sheet. That sheet insulates the warmer water below and miraculously sustains aquatic plant and animal life through the harshest winters. Now, as your mentor, I want to make absolutely sure you avoid these extremely common calculation traps on your test. First, never confuse heat with temperature. Remember our budget analogy? Second, always remember to convert Celsius to Kelvin when you're working with ideal gas laws. And third, when calculating phase changes, please do not use the specific heat capacity of liquid water for ice. The specific heat changes depending on the state of the material. Ice is roughly 2060, while liquid water is 4186. Pay close attention to those details and you'll be golden. Here is your rapid-fire glossary checklist for your final review. Calorimetry is the measurement of heat exchange. Thermal stress is the massive force generated when thermal expansion is restricted. Latent heat is the hidden energy fueling a phase change without altering the temperature. Convection is bulk fluid motion transferring heat. And the Stefan-Boltzmann law relates to the energy emitted via radiation. Definitely burn these into your memory. And there you have it. You've successfully conquered the ultimate thermal physics study guide. But remember, the real test isn't just on a piece of paper. The next time you see a blacksmith fitting a ring, boil some water for pasta, or step into a nice, well-insulated room on a scorching day, I want you to ask yourself, which thermal physics principle is secretly at work right in front of me? Keep that curiosity hot. You're going to do amazing. Good luck on your exam.